time. But, so very warm welcome to all of you today. Thank you very much for joining this webinar. It's part of the UKRI Interdisciplinary Centre for Circular Chemical Economy. I am Professor Benoit Chachouet. I'm with Imperial College London. I'm also a theme leader on process integration and whole systems analysis for the centre. Today, it is my great pleasure to welcome Professor Andrea Ramírez Ramírez. I will tell you more about her in a few moments. I need to do a little bit of housekeeping first. I would like to please ask you to mute yourself during the webinar. And in order to run the Q&A session, what I'm also asking you to do is to please use the chat to write your questions, and then it will allow me to organize the Q&A session at the end of the talk. The other point I wanted to make is that this is a recorded webinar, and in fact the webinar, the recording has already started, so I think I need to tell you that. All right, back to the star of the show today, and I'm pleased to introduce Professor Ramírez. Let me give you a few words about who she is and what she has done before becoming a professor. So currently she is a professor of low carbon systems and technologies in the Faculty of Technology, Policy and Management at Delft University of Technology. That's in the Netherlands. She holds a bachelor in chemical engineering, a master's in human ecology, and a PhD in the field of energy efficiency. The focus of her research is on the evaluation of novel low-carbon technologies and the design of methodologies and tools to assess their potential contribution to sustainable industrial systems. She's been a prolific author with over 115 publications, and she's also the editor-in-chief of the International Journal of Greenhouse Gas Control, which I'm sure is keeping her busy. Incidentally, Andrea is also on the strategic advisory board of our Chemical Circular Economy Center. So her webinar today will be entitled "The System Challenges of de-fossilising Petrochemical Industrial Clusters." So Andrea, thank you so much again for accepting our invitation, and we're very much looking forward to your presentation and the discussions afterwards. Thank you.
Perfect. Thank you, and thank you everyone for being here. I know for many of you it's maybe lunchtime, so enjoy your lunch. I'm just gonna share my screen. Hopefully it works.
Yes, we can see it.
No, you see, I'm sorry, I do the wrong too fast. Now it should be okay.
Yeah.
Did you see it?
Full screen.
Oh, perfect.
Over to you.
Yeah, I think you have two people in the waiting room, but I'm gonna delete that. So thank you for the nice words, and I'm just gonna start. So I was very happy with the invitation to just tell you a little bit about the research we do here at TU Delft, but also what I see are some of the key challenges for defossilizing the chemical industry from a system point of view. It's a little bit of an ambitious title. There are many more challenges than what I can present in 45 minutes, but I just make a selection of some things that I think are nice for thought. Maybe not needed, and I will spend not a lot of time in an introduction, but we know why we are doing this. And the amount of greenhouse emissions that has correctly been emitted into the atmosphere is large and increasing despite going out of a COVID situation. You can see it's a little bit of a complex picture, but you see, the energy use, you see the CO2 actually from industry, so industry related, not to energy use. And you have also all the energy that industrial sector uses, which generates this kind of amount of CO2 emissions. If we look a little bit at, and let me just have my pointer as a laser pointer. I don't know why it's doing this. Yeah. I just borrowed some of the slides from the IPCC 6 assessment report. I'm not going to go again into details, but it's quite clear that if we want to avoid, large impacts from climate change that we are already feeling today, we need to decrease our emissions. We hope to be able to decrease it to keep a target increase of 1.5 degrees. 2 degrees is taking us already with quite a lot of impacts. And this figure just say, what is important is regardless of whether you are going to reach net zero 5 or 10 years later, we need to decarbonize very, very soon. And we need to do that in all sectors of the economy. So unless we have immediate and deep emission reduction, 1.5 is beyond reach. Some people are already concerned about whether 2 degrees will be within reach. So that's a little bit of an alarming system. And we also know that there is no silver bullet. We know there is no one option that will take us there, but it's a combination of options what makes the system or the challenges a little bit more complex. And this is what in the 6th assessment report they have said industry needs to do, using materials more efficiently, reusing, recycling, minimizing waste, using low to zero greenhouse gas production processes. And they also recognize that achieving net zero is very challenging for the industrial sector, so there will be a need also for negative emissions, even if it's just to do some compensation and later to actually take down historical emissions. Now, these are a lot of options. I'm not going to focus on all of them, but I'm going to focus most of this talk in something that UCRI is also working on, and it's around defossilizing the chemical industry by using alternative sources of carbon. And I'm not using the word decarbonizing in purpose because all the most of the process that we have today contain carbon, where is a paints, where is the rubber, the fabrics, the plastics that we use, they have carbon in the molecule. So what we want to do is to change that source of the carbon molecule to have the carbon not coming from oil or natural gas on coal, but we are speaking about maybe using biomass, or can we use CO2, or can we use, for instance, waste? Plastic waste is one option that is being currently discussed. All these new technologies, and you have here the technology readiness level, we will tell you, we'll level the technology fund before commercialization, are what we call early technologies. Many of them are just in the lab. Some of them are in pilot and just moving towards demonstration, but not yet there. So it's a little bit of haste on trying to see how can we take those promising technologies and what are the impacts of doing so. So what we are aiming to do in one side is developing technologies. We also need to implement value chains that takes from raw material to product. Some of them we can use value chains that are already available. For many of them, we will need to design new value chains. And then we need to have full systems. And by full systems, I'm speaking beyond the company. I'm speaking about the logistics, where the raw materials come from, how are my interaction with other systems, enabling infrastructure that will be required, etc. Now, I love the work we do, but I know UCRI also does it. It's called ex-ante technology assessment, and is can we do something with the knowledge we have for those technologies at lab level? And can we use that knowledge to really explore what will be the future performance of those technologies? And we do so in order to provide feedback to the technology developers and to policymakers on how to actually develop the technology further. And to do that, we do a combination of process modeling to scale up results from lab to industrial scale. We assess the economics, we assess the life cycle performance, and we do also uncertainty analysis. And we tend to do ex-ante technology assessment by taking a value chain approach, that is to look from raw material to where the product finish, if possible. Now, I don't know why my cursor is not working, but this was a little bit of a disclaimer of what actually ex-ante technology assessment doesn't do. So we do provide information. It's an exploration of the future. It's for technologies that are early stage of development. That means that we don't know a lot of things. There are a lot of question marks when we are developing the technologies, and therefore there are inherent uncertainties about the information that we are putting into the models. The highly inherent uncertainty means that the results are not aimed to be looked at the decimal point. It's not about the performance. I have something at, in the lab scale at 50 centimeter by 50 centimeter area. I'm gonna design something that works at, industrial scale, and I can tell you exactly, how much will it cost to the decimal point, or how much energy will consume to the decimal point. That is, I will argue that is not realistic and it's not needed. What we are trying to do is to train the insight of where is the bottleneck, where are the problems, what are the order of magnitude, can we do something about it, recognizing that there is a lot of uncertainties and a lot of variables that can influence the result. So that is where the challenge comes from. Now, that means, and I am part of the E-Refinery Institute at TU Delft, and we look at the transformation of, carbon into molecules using renewable electricity, that this is one of the typical illustrations that I have. And this is just, we are going to go from CO2 to formic acid using an electrochemical reactor. And that's how we picture the transformation for the public. And when I see this and, I go into the project, the type of questions that I tend to do are a little bit like this. So it's not only the reactor what I'm concerned about. I'm concerned where is the electricity coming on from, what is the quality, the cost, where is the water coming from, are the critical raw materials used, what is the quality of the product, do I need to do downstream processing to really get it to market standards? What is the infrastructure? Do I need new pipelines? Do I need electricity? Do I need roads? Do I transport by ship? Under which timeline? What are the CO2 impurities that I put into the reactor? Those are system conditions. So even if your reactor is working perfectly in the lab, those are the things that will determine whether or not it can be implemented in practice. So what we notice when we do and look at a lot of techno-economic and life cycle assessment of these low-tier TRL technologies is that they tend to assume no realistic conditions or to tend to assume partial system boundaries. And what I mean by that is, for instance, in the case of electrochemical conversion of CO2 into product, that many studies then assume that the energy is there. I have seen people speaking about unlimited amount of energy that people will pay to use you. Yeah, maybe at some point, some time, but not in a permanent base, because a power company still wants to make profit. Or they tell you the electricity is renewable, come from intermittent sources, by assuming assessment that actually what is happening there is 24 hours, 7 operation. They tend to assume that the CO2 is a gate, that is for free, that has no environmental footprint, that is pure. Some studies don't realize that you need, or don't take into account that you need to do a lot of cleaning of that product that is coming from the electrolyzer to actually get to the product. And from some LCAs, they tend to assume that the phase, that the using phase is exactly the same because of the petrochemical counterpart, which is certain in some cases, but if you change the way you use the product, that may not be the case. Now, I'm not going to go through all of them because there are too many, but some of them just to give you some food for thought, because those are system challenges. And one of those is, I am taking CO2, does impurities CO2 matter? Now, my answer to that, it depends what you want to do with the CO2. These are typical compositions that you will find in literature of fluid streams going out of, for instance, a capture unit, whether it's a capture unit, that you have after having a coal power plant or having a natural gas power plant, or in a cement plant where you have a post-combustion capture, a refinery, a bioethanol plant, or even direct air capture. And you see it changes a lot. So if you want to do something like mineralization, which is converting the carbon into carbonates, that is generally one that is the least sensitive to impurity. You can even put flue gas there, no problem. But if you on the other side want to do electrochemical conversion of CO2, then there are questions that come. Can I put mercury there? If I speak with a lot of the experts, they say, please, no mercury, not even a ppb level. Can I put sulfur there? Can I put NOx there? Can I provide chlorides there because it comes from, biomass CO2? And the problem is that a lot of the experimental work is done with pure CO2, like really, really food degree CO2, which is 99.999% pure, but that's not the CO2 that we will find outside. So without that information, it's not really clear whether we can use the CO2 directly, and if you are going to have a large investment, for instance, an electrochemical reactor, I'm not going to kind of risk it to have a problem with that, so I will put a bench before the reactor, and doesn't matter. So we did a little bit of an exercise to try to compare two different routes to produce methanol. And we were using, let's assume this is a CO2 that has these impurities, and what happens and how it will affect, for instance, the techno-economic assessment. So I'm not going to show you all, the process design and the techno-economic analysis, but in view of this webinar, just to tell you that it does matter, at least in this first assessment. So we were comparing those two systems to produce methanol, one using CO2 hydrogenation and the other going via pyrolysis of plastics to methanol. And what we found actually when we wanted to use CO2 is actually the CO2 purification system that we needed in the kind of option we wanted was around 25% of the levelized cost of methanol. And that is a large amount for a novel technology. So whether it's 25 or 26 or 30 is a little bit irrelevant, but it's not insignificant. This can be done with technologies we have today. That's not a problem, but it does affect your CapEx. It does affect your competitiveness. It may affect which source of CO2 you want to use. And if you affect the source of CO2 you want to use, you may want to have a different kind of, infrastructure. You want to have different regulations for CO2 transport, or there are many system implications. So all I'm saying is that is an aspect that you can just not overlook. And we need people to actually do experiments with impure CO2. That will be a call for all of you who are doing lab work. Try CO2 with different impurity. The more robust the technologies are, the less kind of problems we will have at system level. The other thing that people are doing a lot, and we are discussing a lot, is intermittency. So we hope that in a couple of years, maybe I'm a little bit too optimistic, but by 2050 that we will have in Europe fully renewable, electricity system. Let's assume that is the case. Then the question that comes a little bit in mind is, what does it mean for new processes? So what happens if we have a lot of these CO2-based processes, electrochemical conversion that run in electricity, and you have just this intermittency? Can we actually evaluate the impact, and can we design the process in a way that following the laws? And to do that, we got a project that is partially subsidized by Shell and by the Dutch government to look at what does flexibility mean when designing flexible novel chemical processes, how do different levels of intermittency affect economics and environmental trade-offs, and how significant are system conditions for this. And doing this, we did a review on what flexibility means for the chemical industry. And we found on the one side quite a bit of problems in terminology. So people using the same name for different things, or using the different things and having different, meaning the same and using different names. And that's a problem to actually try to understand what people are referring to. So we published a paper on what flexibility means and how we could have a conceptual framework to develop that. Now, of all the kind of flexibilities that you can have, the focus in this webinar, or what I'm going to tell you in the next slide, is about volume flexibility. And that is because in an electrochemical reactor, if you put electricity or vary your electricity, you can consider it a feedstock to the reactor, then your output will also change. So the ability to vary throughput, we define it as volume flexibility. So we at this moment, JC, which is my PhD student, is working on microbial electrosynthesis from CO2 to chemical products, especially capronic acid. And this is a technology that is developed in the Faculty of Applied Science by the group of Ludovic Jourdain. And he is actually doing the lab work and the scaling up. So you basically put in this technology renewable energy, and you put CO2 on water, and the cathode, you have microorganisms, and they do the conversion, and you produce, for instance, caproate or caproic acid, as we are at this moment analyzing. And we are using this just as a case study to try to understand how to design flexibility. And then we say, let's assume that electrolyzer, which is an assumption, is completely flexible. What happens afterwards? What happens with the rest of the plant? Will that be a bottleneck? And the answer to that question is yes, it will. So you have to assume, for instance, these bio-based products produce very diluted products. So in this case, 10 grams per liter of caproic acid, and you need to sell it at 99%. So if you want to do that, you actually have to take a lot of water from the system. So to do this, we use a liquid extraction to just take, to be as energy efficient as possible. And then we just spent, I think, a year trying to understand how to model the flexibility of the different units to understand where the bottleneck are. Here you see, which units are consuming the more heat. And it's not such a simple system. The economics are also problematic. But when we wanted then, and that's what she did, she changed the amount of electricity going into the system, which changed the load rate going into the different equipment. And as a consequence, your equipment is not working at the design capacity. So it's working at different capacities, and every equipment is different from others. So some equipment are more resilient. Some of them, you really need to keep it really close to design, to the design system. So Jessie was this week in the SCAPE conference in Toulouse presenting the results of this part of the work. And what we found is the volume flexibility of the downstream processing was 70%. So that means I have a 30%, I can vary my load rate with 30%, and still the equipment will work, but it will not be as efficient. It will have a cost. You are then operating a little bit more inefficient, but you could operate. Below 70%, my equipment is trying to have really big problems, especially the hydration unit, and therefore I needed to shut down. If you consider that, what happens is in a year, having a profile like this of a wind plant, if you don't do anything, this kind of design, you will be shutting 3,700 hours a year. If you consider that a year is 8,000, it's something 1,000 plus hours, you are shutting quite a bit of the time, and that will kill your economics. This is a CapEx intensive process, so you would like to run it as much as possible. So the second question, and that's what she's working at this moment, is, okay, how can we increase the running time if you have this kind of profile? You can do several things. Remember, in our assumption, the mess is flexible, and we only have the possibility of intermittent renewables. So one thing we try is to further electrify the downstream processing using electrodialysis as a pre-concentration step that has been done. And the other thing that we are doing is actually adding batteries and buffer tanks to try to minimize the variability, and then do a techno-economic and life cycle assessment to assess what happens. So basically, you have intermittent electricity in the one side and caproic acid in the other side. You have an electrolyzer in the middle that doesn't accept as much variability as this one in this case. So we will put, a battery to reduce the variability, and then some storage tanks. You can make the battery very big and the storage tanks very small, or you can make the battery small and the storage tanks bigger. All these have influence in your CapEx and in your OpEx. And also actually in the physical footprint of the plant. You can finish with storage tanks that are bigger than the plant, and that's something that you will not like. So this is what we are optimizing at the moment, and we hope to have a paper with the results by the end of the summer. Now, in the second part of this talk, then I have spoken a little bit about what happens with these technologies when you treat them as a technology standalone. But reality is, and if you go in the UK to different of the industrial cluster, that's where the industries are located. And most industries are located in highly symbiotic industrial clusters. They are not located isolated with some, exceptions. But at least in Europe, in the Netherlands, they are really clustered. And therefore, the decarbonizing power, so, taking the fossil fuels from power and the fossilizing process impose challenges because of the interconnection that happens at different scales. So let's assume You do an evaluation of a novel technology for a petrochemical industry. And generally what we tend to do is what we call transmaterialization using a vertical evaluation, which is basically you take the current system and you have a portfolio of technologies, A, B, and C. You do, your techno-economic, your life cycle assessment for each individual route, and then you compare the performance and you choose the best one. Then you say, to replace the fossil raw material, I will use, for instance, option C because it has the lower cost and the higher avoidance of CO2 emissions. That's okay. That gives you a lot of insight, this pairwise comparison. It does assume most of the time that you are in a green field where you are just comparing two novel technologies. Now, what we have done in the next project that I'm going to introduce is to say, wait a second, this is good, but that's actually not how the industry works today, especially the chemical industry. So this industry that I'm trying to defossilize in my system, if I go to the location, I may realize that that company that uses fossil fuel actually is providing waste heat to a second company, just selling the waste heat, to produce a different product that has nothing to do with my initial product. It's just selling the waste heat. What happens when I actually take out the fossil process and put a new process? For instance, that would make it out of CO2 and make it with renewable electricity. Well, that waste heat will be affected, most likely disappear. And then what is the second company gonna do? Is it gonna use natural gas in the worst case scenario without CCS? That will imply that all I have done is shift my emissions from company one to company two. Can this be solved by this one using a lot of heat? Of course, but it's not like all the companies speak all the time to realize if I do A, you will do B. It may be that this will be the option of the second one, and therefore you have invested a lot of energy here, but only move emissions at a higher cost at the next side. So to assess this, we have gotten a project, which is a personal grant I got a couple of years ago from our Dutch Research Foundation to look at the impacts of using alternative raw material industrial clusters. So we wanted to actually be able to assess both all your vertical impact from life cycle assessment with your horizontal impacts from symbiosis, and try to understand how flexibility or how integration in the industrial cluster or symbiosis of the industrial cluster could be affected by this transformation that we are going to do. Is so in which way, for what kind of companies, what kind of technologies or new technologies do they all affect in the same way, or do they affect in different way? So the focus of this project is not in the energy side, although energy is of course a consequence of the model, but we are really focusing on changing the source of carbon in the cluster. So if you speak about what is new in this project, is because we are studying both the vertical and the horizontal impacts, and we are studying the transmaterialization of clusters. And because I have here in my bar the Port of Rotterdam, that is the example that we are taking as trying to model to. The Port of Rotterdam is only 40 square kilometers in area, and it has 5 refineries and 45 chemical industries and 5 biorefineries. So you can imagine how concentrated and interlinked is everything. So the first step that took us almost 2 years, and we have completed by now, we have developed a twin representative model of part of the Port of Rotterdam. So we have selected main processes, main products and byproducts that exist in the port. We have kept the production capacities that in the port, and we are mimicking the real interactions between different industries that we see in the port. We are mimicking in the model. In the cluster, in our toy model, in the cluster, we are going to call baseline cluster from now on. We have modeled 6 industrial sites with 20 different companies, around 57 chemicals. We have grouped as they are grouped also in the cluster in Rotterdam. I would like to know several things because it allows you to understand a little bit what we are doing. Every petrochemical process has been modeled as an independent model. So it's not a super model in terms of optimization of the whole cluster, but it's a modular model. Why? Because that's the way the cluster works. You know, every company optimizes for themselves, not for the whole cluster. We are modeling in Aspen, so it's process modeling bottom up. The individual models already provide us quite a lot of insights because it allows us to get really energy and mass balances of the today condition. We can get of emissions, we have area footprints there, we have equipment costs, etc. And we are going to make the whole model open at the end of the project. Therefore, from the very beginning, we spent quite a bit of time developing model and reporting strategies that all the modelers involved in the project are following, so that regardless of which model you open, it has been modeled in the same way. So this is a little bit how the whole model looks like. I know you cannot read a lot of the boxes, so if you allow me to zoom in a little bit. So for instance, this is what we call the chlorine subcluster, and then you see all the boxes that you see here are individual models. All the arrows that you see here are, you know, main products from this, for instance, chlorine that you produce in the chlorine company here is being used to produce ethylene dichlorine in this company here, and so on and so forth with all of them. So if I will zoom in again, in one of the boxes, then you will see an individual Aspen model of that process that we have verified then to be representative of what we have found outside. So how do we do that? We have people just looking for several years in all kinds of reports, websites, books, permits that the people ask when you have to do a plan to submit a permit, or you ask for a permit to the government. Some of the information is open. You will have to use all that to actually try to mimic as much as possible of what's going on. But you know, in a cluster, companies are interconnected by more than only the main products I just showed you. So Paolo Ibarra, which was a postdoc in the project, spent also quite a bit of amount just trying to map all the utilities that are shared between companies in the real cluster so that we could mimic them in our toy model. And we're speaking about things like oxygen or argon or nitrogen or steam or waste fuel or water. So it's quite a lot of digging information just to try to reflect the complexity so that we can actually assess the impacts. Because we have energy flows being there, we have also modeling apart the utility islands of the different companies that are using information from literature, and conducted also a basic pinch point analysis to understand whether we are underestimating or overestimating the amount of energy that is used by the companies. We compare the energy from the process models with the energy that we found in reports from the companies and try to see when are they close, when are people buying energy, when are people producing energy inside the cluster. And based on that information, then we develop 24 models, which are then the energy production models in the model. Not just to confuse you, but then we have individual utility islands that give different kind of steam or electricity to different companies, and a part of that, we have all what is bought from outside our cluster. Why do we want to do all that? Now that you have this kind of model at that level of complexity, then we can do things like this. You can do material flow analysis for the whole subcluster, or for the whole cluster, and this is just an example of a subcluster that was done by Michael Tan. And you see here, for instance, you can do network representation, and if you can do network representation, you can use a lot of graph theory to analyze where are the most important nodes, where is the carbon going to, where is it moving from, which are the most interconnected paths, what are the isolated paths. So you can do also risk assessment. You can do carbon flow analysis, telling you, you know, where is the carbon that is going from the olefins, who is using the more carbon. And remember, this is only for the subchlorine cluster, but we are able to do this for the full cluster. We can also do water flow analysis. So you are able actually to get also an information at the system level of how are things distributed in this cluster that you could not do otherwise. Now that we have that, then I have 3 PhD students working on this model. Tony is going to be looking at decarbonizing chemical building blocks. So to see what happens when I change my ethylene or my propylene and how the impacts propagate in this symbiotic cluster. The other PhD, Ina, is going to be looking at what happens when we actually transform the downstream processes. So I'm not going to be changing directly, ethylene, but I'm going to be changing the way I produce PET, or I'm going to do something different on my downstream side, because the impact propagation upstream are different than the impact propagation downstream. Well, at least that is the hypothesis we want to prove. And then there is another PhD, which is Michael, who is really joining all this and doing more full modeling using superstructures to understand how the paths move. So, as I said, you have Tony doing the chemical building blocks, and we are starting right now with decarbonizing ethylene. And Ina is at this moment looking at MTBE. I think this one is her first case study. And what they are going to do is we select system products in total, so 8 chemical building blocks, 8 downstream derivatives. Each of them is we are selecting one alternative of how to produce ethylene from CO2, how to produce ethylene from biomass, and how to produce CO2 from waste, and then doing the same with the different chemical building blocks, and then having a total of 48 alternatives you can put in the model. To do that, you need to develop a pre-screen methodology, because there are many ways to produce, for instance, ethylene or propylene. So we needed to do a little bit of systematic work on how do you select things, because we don't have the resources to, model every possible technology is needed for the goal of the project. So just as an example of how complex it could be, this is part of the mapping that Tony Manaral did in order to understand which pathways were there to make ethylene from alternative sources of carbon. And we found 54 possible pathways. And I think that's part of the challenge that the industry has today, is how to select from these kind of big clouds. And from here, we have select 3, as I say, 1 route from CO2, 1 route from biomass, and 1 route from waste. And then we will do a model at the same level of detail, so Aspen-based than the original one, and then we can replace it in the cluster and start, we are developing the methodologies to look at the impacts. Something maybe that I forgot to say is if you look at this cluster and there are things coming from outside the cluster, so feedstocks that are not produced in the cluster, we have linked the model to a life cycle assessment to EcoInvent database. So every product that goes into the cluster has an environmental footprint. And we do that because we want to assess whether decarbonizing de-fossilizing the industrial cluster will actually just increase CO2 emissions outside our system boundaries. We want to look at things like level of synergies, or how to replace targets, or where are the bottlenecks, are technologies playing together, are you getting lock-ins, can we identify lock-ins in advance? And we think that's information that you will need if you really want to transform the industrial sector radically, the chemical sector especially, towards the targets in 2050. Now, the 3 PhDs I described right now are only working with the mass flows, so decarbonizing the mass flows. But what about decarbonizing the energy? And because we already have this map and the whole work put in this model, we can also assess that. So there is a different PhD as part of a different process that is look at how will strategies of decarbonization of more the energy side will affect the chemical industry if you do it individually or if you do it at cluster level. What are the economies of scale that you can actually identify? So she's going to take only the ethylene subcluster of the model, and she's going to begin to play with scheduling and power system modeling to really link what happens if I produce, if I electrify all my steam, or if I use hydrogen, or if I combine the two. And she can do that for every individual plant. And then she's gonna do for all the cluster, because also we have geographical distances between here in the model that we have reported. And then you can see whether economies of scale or sharing infrastructure will be beneficial, and if so, what and when. And she's going to start first only with the utility units, and later she's going to look at the models that the other PhD has developed and try to see what happens when you change the process. So a little bit more short term, where you can really move utility units, which will be a little bit of the simple option in the short time, compared to a more radical observation of having a completely decarbonized option. So I think what I try to tell you is, I mean, it's a complex picture. I think we are getting a better way of what to do, but there are a lot of technologies in the chemical industry that are at this level. And in order to really understand what happens, I think you need to go from, understand what happens at process scale, understand what happens in the potential supplies, then try to understand what happens in the socioeconomic system, and then actually figure out how to use this information to be sent back to the lab scale or to the demo scale, so that we can change technologies in the places where we have the largest degree of freedom at the lower cost. And that is when the technologies are being developed. Once they are developed, yes, we can change technology, but that costs money. And sometimes they also cost so much money that you make them unviable for a given system. So we hope that the methodologies and trying to understand technology from a system point of view will help to accelerate, the transition of the chemical industry. Even though it looks like I'm putting more problems in the table, I think we have the tools to start treating those problems one at a time, especially if you have, consortiums like UCRI, or the work that is being done in the Netherlands, where we join forces to try to understand better what is happening. And I do not want to finish. We are saying, of course, I didn't do this all by myself. And all the work I presented here is done by Parma on my group. I didn't present all the projects that we are doing right now, but just a shout out to all the people who have been doing really, really nice work in the group. And that is it. I don't know how I made time, or I speak in the Spanish speed and went super fast. But
you're doing great on time. That's why I didn't interrupt you, Andrea. So we're about we have 16 minutes left for discussions, which is great. So first of all, thank you very much. I think we can use the clapping thing in the on Zoom to thank you for your great presentation. I think it's really an excellent overview of for the research projects and ongoing directions you're taking in your group. Personally, I'm always very impressed to hear you speak about this modeling or digital twinning of the Port of Rotterdam, the whole Port of Rotterdam. I think that's really impressive. So I'm once again, I'm asking you if you can please write your questions on the chat. I see Mehmet Merkan, he's a colleague of mine at Imperial, and he's asking you, Andrea, trying to understand better what is the motivation really behind trying to substitute fossil resources as feedstock, because his point is that they don't directly lead to carbon emissions, right? So he's saying, why do we care substituting fossil resources?
Well, they don't, thank you for the question. They don't lead maybe to carbon emissions in the cluster, but they do lead to carbon emissions. So if you look at plastics, and it's a typical example of all the amount of plastic that we have produced worldwide. And it was a really interesting paper of 2017 by Greyer and al. that just showed that only 10% of the plastic has actually been recycled. Of that 10% or 9%, only 1% has been recycled more than one. That means that you have around 90% of the plastic that is going into a landfill, and a lot of the plastic, 60%, is actually being incinerated. So, and that incineration finishing CO2, biodegradable plastic sometimes degrade into methane. So when you go beyond the industrial cluster, you say, well, that in the timeline of 5 years or 10 years or 15 years, the carbon is again going to the atmosphere. Can we change that? Can we use other source of carbon? And
that's
make
the time
sense.
scale, isn't it?
Yeah.
Because that carbon in plastics is already there in a way, right? It's already been extracted, it's already been processed.
No, so it's a way of recycling. So at least avoiding fresh use. That is the one side. And the other side, I'm not saying CO2 is always the answer. I think in some process CO2 is going to make sense. In some process biomass is going to make sense. In some process waste recycling is going to make sense. In some others, it may be that even fossil fuels may be sense with CCS in some particular instances. I think we just need to evaluate what happens and how much energy you require and what are the efforts needed to actually do that transformation.
Thank you. I also had a question that was, perhaps a bit of a follow-up to that, because when I look at refinery petrochemical complexes, these are highly integrated, right? So it means that if we start disrupting this integration by, for instance, displacing the carbon feedstock for the petrochemicals, there will be a cascade effect where there will be some rebound effects as well.
Yeah.
And that's notoriously difficult to predict and to take into account. So just wondering, especially on the supply chain level, what is your opinion on this? How to best handle this kind of effects?
Yeah, well, that's exactly what I'm trying to leave my share screen. You see me people fiddling around. It's because I want to have the full screen. I don't manage. I don't know where is it. I'm still sharing my screen.
You're still sharing your screen, yes.
I have no idea. I don't know why I cannot unshare. Maybe you need to stop sharing my screen. I can. I lost it's only 2 years of COVID, so that's also why I don't. Apologies for this.
That's okay. I was just trying to share my screen to help you stop sharing yours.
Perfect.
Okay, there we are.
Perfect. So that's actually the motivation. I think at this moment, of course, look, what happens in a lot of us now, you want to integrate because it makes sense to use, material efficiency and energy efficiency is about integration. So we have also at a European level, a lot of, incentives to use as much and to develop industrial symbiosis. That has influence in the value chains and how you have developed the value chains around centralized focus, allow economies of scale, and we keep, and is the short-term option is to use what you have at hand. So we keep integrating more and more towards 2030 goals. What the question we have is that integration going to be a lock-in to actually transform radically towards 2050? The more you integrate, the less flexible you are, the more dependent you are in others. So that is part of what we want to assess. How flexible is a cluster that is highly integrated, as is the Port of Rotterdam? How can you identify that? Where do you begin to see the problems? If we can't see problems, can we put buffers? That will be after the project because it's a little bit ahead. But can we figure out a way to do material efficiency and still not get in a lock-in situation where you are not allowed to do large transformation later on because you have put too much money doing integration right now? And I don't want to say that you don't need to integrate. I'm just saying you need to be careful of what happens after 2030 when you want to do full transformation.
Yeah. So it's So what you showed, if I understand, the Port of Rotterdam is looking at the cluster scale, right? And you're saying that of course you're going to connect that to all the bits of the supply chain, and that's a multi-scale problem, isn't it?
That's a very multi-scale problem. So we are doing it a step at a time.
All right. I see in the meantime there's another question in the chat. Do you want to unmute yourself and ask your question? Do you mind doing that?
Is it me? I guess.
Yes.
All right.
Thank you.
So thank you, Professor. Excellent work, and I can also see, students who would be kind of making all of these PhDs in the next few years adding to more to that knowledge. My question is really the thinking on sustainability seems to be leading at a much faster pace than activity at scale, which is at the industry scale and so on, while we have demonstrators happening everywhere. My real question is, how do we really hasten the gap between the thinking and the high quality thinking versus the rate at which practically anybody is able to follow it at scale?
Oh, that's a very nice question. It's a very it's a difficult one, because the level of abstraction is different, but also because I recognize the questions that we look from a system level may not be the question that you have for an individual company, and that's the problem. You are interested. I'm interested, or maybe the Port of Rotterdam as a management institution is interested on decarbonizing the whole system and de-fossilizing processes. But I, as a company, I have a different interest. I want to, maybe de-fossilize here, or maybe decarbonize there, and I'm not optimizing to the rest of the system. If another company, which I'm not legally attached to, happen to increase their emissions because of my decisions to defossilize, that's actually not my problem. And I think that, and they don't have the overview of what are the consequences. So the first thing is for me, at least from my role, is to try to identify, is there a problem? And if so, how can we make it visible? And what is then the interest of different members to answer it? But I don't know if that answered your question fully.
No, thank you. I think it does put a perspective, and obviously all of us need to work together on it, but very excited to see your work. Thanks so much.
Thank you.
If I can add something and do a bit of self-advertisement, because as part of our center, we have a theme that that I'm leading, and that does a lot of this techno-economic and environmental assessment in the same way. And then there is, as you know, Andrea, there's a theme on business and how to do sustainable business, how to finance this circular economy, and I think that also connects to to this question, how to make it happen in practice. And that's a different dimension, isn't it?
And I think a main thing, and I didn't have it as a slide, but there are no inherent sustainability. So a technology is not inherently sustainable. It's the system that is sustainable. That means that you need the technology in a given context. So circularity per se does not decrease CO2 emission unless you put some conditions on how the circularity is implemented. CO2 utilization may result in increasing CO2 emission unless you take into account what are the energy sources I use to actually, capture the CO2 and then make the product. So sustainability is so context dependent on systems, a system concept, as is, carbon neutrality and carbon negativity, that technologies play a role, but not the key role. You need to look beyond the technology to understand whether the system is going in the direction you would like it to go. That would be my argument.
Mm-hmm. Now, a lot of questions are arriving on the chat, so I apologize if we don't have so much time left. So I'll be cherry picking. That's bad, but I need to do that. I have a question from Valerie Pinfield. She's asking regarding the fluctuation in electricity supply. She's asking whether, in your opinion, it ultimately will be handled more at the supply chain level or at the customer process.
Yeah. So what is interesting, because Svenja went and spoke to power companies and to chemical companies, and the expectations are really different. Sometimes, like, you guys need to speak to each other. So if you look from a power company point of view, they will do, some management. The more they need to store, the higher the price of electricity is going to be, because you will be, you need to be certified to get this amount of electricity in an intermittent system. So you need the storage. They can take part of that problem. But you speak with power companies here in the Netherlands, there is the expectation that there will be a lot of demand side management to try to balance the grid, to help in the problem. And that will need a different market mechanisms for electricity. There is people in my department looking into those market mechanisms. I was a little bit more concerned with the question of whether actually the company could actually do this and the process could physically do this. when we spoke to the companies, they were not as enthusiastic. Because it will mean a higher risk. They don't operate the process in that way. And what will be the profit of not producing? You know, what do they get if they shut down? They have the capex. So they wanted to understand under which conditions and what market mechanisms will be there in order for them to do that. So you need like these two different sources, and where do you want to pay and what do you want to minimize in case of risk? If you really go to electrification of processes, high variation of prices is a big risk for them, for production costs that they will try to minimize. Long answer, sorry.
No, thank you. And then I have quite a number of posts that are connected to your case study on the Port of Rotterdam. I think a lot of people are indeed interested in that. First one is a comment by Marc-Olivier Coppens, who's saying, perhaps game theory could be used in order to see how individual companies manage in the port. So it's not a question, it's more a comment. And then here I have a question regarding the setup of this huge case study. How so Abigail Bell is asking, do you have any advice on how to obtain inputs, outputs, and process data from companies in order to create such a case study? That's a huge effort.
So we hope we are making open all the data we get, that is going to help many people, but it will take a couple of years yet. Look, I went very, very practical because I wanted to have open. I was aiming to do open source from the very beginning. We avoided going to the companies and asking them for the data because that will come with an NDA. So we asked money within the project to do, to just literally go and try to get data. And that implied a lot of report reading. And I think now that we are doing verification, so we go to companies and ask, or discuss whether this is representative of their sector. It's not one-to-one. We have some freedom in the design. They are sometimes surprised of what you can find in internet if you are patient enough. So it's a lot of data mining you can do because people publish more, including companies, that they think it's all over the place and you have to have the patience to just go through it. That's easier for the situation as it is right now. It's more difficult for the novel technologies because they tend to be protected under patent or proprietary information. So we do, patent-based or Aspen-based modeling, and it's more uncertain. So how to do error propagation in the model is one of the key questions that we are trying to handle at the moment. Mm-hmm. So patience.
Absolutely, yeah. I'm interested, in the interest of time, maybe I can invite, I see Katie Armstrong had a question which is quite long. So Katie, if you're okay, if you want to unmute yourself, and then perhaps, that will be the last question today.
Hi, Andrea. How are you doing?
Hi, Katie.
Thinking about the whole systems approach, because your diagram showed how all the industries linked together down the really long supply chain. How do you think emissions reporting might go in this, when effectively you're taking the emission from the upstream in the chain and passing it down the chain to the end user, who then might make an organic chemical that then degrades? Should they be responsible for the emission that's saved further up the chain? Or how do you think this might work in a real practical way?
That's the key question that has been on the discussion, and it has been a lot of discussion. Who has custody of the carbon? And it depends. Are you getting credits assuming that the carbon never gonna go up? So if you are getting money or credits for the carbon never going up, then most likely you are getting the custody of the carbon, and then it becomes to be a problem, especially in circularity, because the carbon will go on back, and who follows that? And I know there are people trying to see whether blockchain or something can be done to follow custody. I'm just afraid the system is going to be that complex. It's not going to work, and you may want them to have a different approach, which is to guarantee only, to have less credit, but guarantee you custody only for a limited time, and try to incentivize other actors to take part of that custody at a price. But I don't have, I know it's one of the questions we have been thinking about, but no answer.
My worry is it could stop development because people can't do it because they still have to report the emission at the end. So you make slightly perverse decisions.
Yeah, exactly. Or you will need to, you will need to sign that you are guaranteeing. How do you dare to guarantee, especially if your product is going to go through several value chains and you don't know where it is? So it's a very interesting, but I think it's a bottleneck that we need to solve. Otherwise, we need to look at the system, so the credit system, especially in circularity and negativity, in a different way. But that's a question.
Thank you very much.
You're welcome, Katie. Nice to see you. And I'm just going to answer the one I saw in the chat, because Lei is asking a technical question. We do not know. Aspen will not be able to, maybe somebody from Aspen will kill what I say. I don't think it's practical to have like a super model that has been treated before, to try a super model with all of the Aspen models within one and then do optimization. I think that's not a feasible way. And I think it's unrealistic in another sense. I think what we have done is treat the Aspen models as different companies. So keep them separate and actually send the output in an interface. That's also why we use in superstructures that allow you to actually group and optimize, and then you have to send information back. And the reason why you would like to do that is because a company does not optimize for other company. I can repeat, they do optimal solutions at company level and suboptimal at system level. So you want to keep that on hand. You don't want to assume that everyone's sub-optimized and there will be companies losing because they will be there to lose. That's not realistic. So I will not go that way. I will just keep it separated and work in an interface that allow you to exchange information. So basically, what you do with the Aspen is to control that you have good knowledge on mass and energy balances. That's basically what you are doing, trying to understand where are the efficiencies coming from.
And if I may, maybe it's also algorithmically preferable to do that, right? Because you could always, I suppose, develop surrogates afterwards if you want to drive, superstructure optimization.
Yeah, yeah, absolutely.
All right. So at this point, I believe that everyone will, join me to thank you, Andrea, again for this truly excellent webinar. And thank you all for attending this kind of inaugural webinar in the center, and enjoy the rest of your day. And my understanding is that a recording of the webinar will be available, so we'll be able to access again.
Thank you very much. Very, very nice, and I hope to see you at some point in real life.
Now that travel is also resuming, yes, very much so.
Perfect. Thank you.
Thank you, Andrea.